let's see where to start. I think the first thing to start by understanding is, this thing we call computation is a fairly new thing. Maybe not to you guys because you're young, but this idea of thinking about the world computationally is something that is a few decades old. And it's something that is kind of becoming clear that it's kind of the dominant paradigm of the 21st century, to kind of take whatever field one's seeing and think about it computationally. That means kind of to have a structured way to think about the field in terms of things like rules and so on that one can describe in a computational fashion. I think the kind of the cursor to this, what we saw with mathematics. And maths, originated a few thousand years ago, and really serious after something that had happened 400 years ago, which was the invention of mathematication. I mean, before time, if you wanted to talk about math, you would be describing things in words, and that was a medium for describing mathematical kinds of things. And then people started inventing mathematical notation, and plus signs and equal signs and things like that came into existence. And what that did was to kind of streamline the exposition and communication of mathematical ideas. And that notion of kind of the creation of mathematical notation is what launched algebra and then calculus, and basically made possible what are now the mathematical sciences, so to speak. So that's kind of been a big thing in kind of the history of formal thought, is this idea of mathematical notation. As far as I'm concerned, the thing that I've been on doing the last 40 years or so is trying to make similar kind of notation for computational kinds of things, a kind of a computational language to present things as in the computationally, to provide kind of a bridge between what we humans think about and what is in principle possible computationally. I kind of view our computational language, Wolfram Language, as being an attempt to take things that exist in the world, represent them computation in a way that we humans can think in terms of and work with. And our effort in kind of build this computational language has been sort of a unique and sort of, in a sense, it's strange that this is not an idea that other people have had. And I could it's interesting that it turns out in the world there are ideas that just don't have they don't occur that many times. And this notion of kind of make the world computational is something which there's been much said about why that's basically a good idea. The hard work of actually trying to do it, trying to build a language that represents that, we're kind of the whole story of that. And it's just different from what's happened with, for example, programming languages. Programming languages have had a different objective. I mean, programming languages arose from the early days of computers. In the 1940s, 1950s, kind of the goal was, we've got this computer, it's got certain hardware, it's certain registers and instructions that are, let's find a way to let's tell the computer what to do. It's a different objective from let's take the world as it is and try and describe in this paradigm, is this computational paradigm. And so what's happened with programming languages has tended to be that the constructs that exist in them are very much based on things that were built into the early hardware of computers. Whether the hardware of computers will remain the same as it's been is an interesting question. If we had, let's say, molecular computers from the very beginning, would we have had anything like the kind of constructs that exist in current programming languages? But kind of this arc that's lasted, I don't know, for the last 60-something years of sort of programming language development has been very much in the, there are variables, there's memory, you're storing things in a computer, you're specifying instructions that are being done in a kind of a sequence of steps and so on. This is kind of the story of what programming languages have tried to do. And programming languages have generally not tried to represent things about the world. They've been concerned with representing things that happen inside a computer, not that exist in the world at large. I think that the thing that let's see, is there a problem with the audio? Sorry, I was just noticing.
Yes. I think there may be a slight echo.
From me or from? I can hear you guys perfect. Let me just see.
Well, actually, it seems to have gone away now, so I'm not sure.
Okay. You sounded so perfect. I assumed that I was similarly perfect. Okay, well, maybe well, let's see. So, I'm not quite sure what you guys know about, don't know about, etc. I could try and let's talk a little bit about where to start here. Talk a little bit about language and the structure of it and how to think about its design. We can talk about how it's to kind of broader idea about computation. Maybe we start off with kind of the concept of Wolfram Language, which is representing think computationally. So if we take capture let's just cap some random picture here. Let's say, oh, there we go. There's a picture. Let's paste that. We could say something like, we could take that picture and we could say, do an operation on that picture. The concept is that any of these kinds of things, that any kind of construct that is the type of thing we humans care about, like pictures, for example, something that we can represent computationally. Now, we might have some operation, let's say nest list. So that's a typical kind of operation that is a sort of general symbolic transformation. I should explain that one of the sort of key ideas of Wolfram Language is it's a symbolic language. So the X is just a thing that stands for itself. This picture is another symbolic construct, just stands for itself. If we have something like, I don't know, the country Canada, for example, that's a thing that just stands for itself, and we can say, for this particular thing, we could say something like, what's the population of thing, and we'll get some result, or maybe we can say the what's the time series of population of Canada, and we could say, I don't know, let's say something like this, that will show us that will again take this thing that is a representation of sort of something in the world, a people as a function of time, and be able to compute with it. But let's say we go back to this picture, and let's say with this nest list, we say we take this picture here. We could say, for example, let's just nest list edge detect that picture 5 times or something. Now we'll get it to 10 times, let's say, and this will now give us. We're just taking this thing, this sort of construct in the world, and we're doing this operation on it. So similarly, we could, for example, we could say what kind of, we could deal with all kinds of different types of constructs. Let's say we have a graph. Let's take what can we do here? Well, so let's start off with something very straightforward. Let's say we have a random graph. We now do some operation on the random graph. I don't know. We could it's a typical one to do is like a community graph plot, and that will take this graph as a thing you can deal with computationally and operations on it. We could, for example, say we could take let's what can we do here? We could take some sorts of different things. We could take let's take something like this. Let's say countries in Europe. So what we're doing here, this is kind of interesting in sort of language design kind of way, we're using natural language to specify something ultimately becomes a precise piece of symbolic language. So that thing I specified in natural language turned into this symbolic object that can now be manipulated precisely by Wolfram Language. So I could say, for example, here, let's say I just say, for example, this. Take this. I could say I could get images of flags here, for example, and I could do something like take those flags and make, I don't know, some chromaticity plot, let's say a 3D chromatic plot of those flags, and that will give me the colors of the flag on. But the point here is that we have these kinds of things like flags of countries or like themselves, that are things that exist in the world, and we have a computational representation of those things that we're able to manipulate. And kind of the core structure of what's happening here is we've got the symbolic language, and the only operation really that this language does is to make transformations for symbolic expressions. So if we say, you know, what is the how would we sort of define things here? We could say, for example, let's say we want to define a function f. If we could say a function f where there's some x blank goes to x squared, for example. What does this mean? This means every time you see an expression that has the form f of blank, where blank is named x, and f of that same blank, transform that to x squared. So if I say f of the list, you know, 8 or something, turned into that. If I say f of let's say, for example, here we could say that flag, it'll transform that into that took the image and squared it. I guess we can, let's see what happens with that image, because you can do operations on images. So you can say something like, I wonder what we can do if we say, actually, I'm now very curious what happens if we were to say 1 minus that. What would happen there? Oh, look at that. That's fun. But the point here is that the basic operation of the language is just to take symbolic expressions that match this form and transform them in this way. And that's, in a sense, all the language ever does, is to take symbolic expression and transform them according to rules. Now, what's happened over the last 40 years or so is that we've built up a huge collection of kind of built-in operations that we use to transform things. Let's see what happened here. Did I open this on some other screen? Maybe so. And for you know, lots of different areas, whether we're dealing with, I don't know, geometric things, or whether we're dealing with things about medical data or whatever else, there, you know, we can say, if we wanted to, we can say something like, you know, left hand, and we could say something like anatomy plot 3D, and this would be yet another kind of structure that we can represent symbolically and do things with computationally. At least you can load up the data from this. There we go. So one of the things, so what's involved in creating this language? Basically, what one's interested in is asking the question, what are sort of all the kinds of computations people might wanted to do? And there's a whole vast range of those kinds of computations. And my goal, for example, has been to try and identify sort of the loops of repeated computational work that people care about doing, and who basically give those themes, those words in the language effectively, and then implement that corresponds to the constructs and operations and so on. There are about 7,000 kind of built-in functions, constructs like whether we're dealing with images or sound or strings or geometric objects or videos or whatever else. There are about 7,000 of these kinds of things cover the kinds of things that we can represent computation. It's sort of interesting to compare that, you know, in English, there maybe 4,000 words, maybe 5,000 or 10,000 picturable nouns, things like that. It's interesting to compare the kind of magnitude of what we can represent computationally with the types of things that exist in natural languages. We've got a fair distance towards sort of being able to represent the things people care about in the world computationally. So one of the questions then, so the thing for me that's been kind of a key aspect of doing this is what is involved in this process of language design. How do you decide, say, how to represent date or something in language? You know, we can say there's the date. No, there's today. What's involved in representing something like this in a symbolic way, and inventing things like I don't know regularity of date, whether a date is we say something like I think we could probably say something like date object now. I could say century. I mean, that's a date that corresponds to something with a granularity of a century. And if we would say that minus now, I wonder what it'd say. It says no centuries, right? Because that's its best representation of the moment now, subtracted from the thing that is a century, as you know, a time represented on a granularity of a century. But the thing that's sort of been an interesting process here is the problem of sort of designing computational language. It's kind of purist way I know of kind of being involved in understanding the essence of things is, because to sort of design this kind of broad computational language that presents a kind of a thing in the world, you really have to understand that thing in the world works to be able to do that. So, in fact, for those who are interested, I am one of my curious habits over the last few years has been that let's see if I can pull this up here. We have been live-streaming many of our internal design reviews for Wolfram Language. So, oh my gosh, that's outrageous. But 636 of these things, of all sorts of different things that we're trying to design. And this is sort of I don't know any other kind of place where you can actually find out what's involved in kind of this process of kind of figuring out the functional design of something computational like this. Well, maybe I should say something a little bit about kind of well, the thing that's been interesting, this kind of symbolic programming paradigm for representing things in the world. I kind of started doing this 1979 or so was my first foot in building computational language like this. And the thing that's amazing, this kind of idea of represent things of symbolic expression. I explain everything that we're dealing with here. Kind of, you know, we've got some construct here, and the thing is a symbolic expression that is always represented as these heads of arguments. So, for example, I'd say if I wanted to, I could say, I could see what this looks like. We could say, what's the expression tree associated with this? And actually, I think there are many different forms of expression tree, but there's a sort of simple version of this expression tree. Everything is getting represented in this very uniform way as a symbolic expression. So whether, for example, this very document, if we were to look at that, if I were to go sort of behind this notebook, and I were to say what's really here, it too is a symbolic expression just presented in the same fashion. And so that uniformity of expression is what allows a limited set of operations and a limited set of sort of concepts to apply across the whole system. And that's what sort of critical in the learning of a system. There are a limited number of mental ideas that just get applied over and over again. And it's kind of a big heavyweight thing to produce another kind of fundamental idea in a system. We try to greatly limit the numbers. It's probably I don't know, one a year or something at most that we've introduced over the 35 years that Wolfram Language has existed. There are thousands and thousands of specific applications of the core principles, but a very limited number of new principles that are relevant for the kind of core structure of the language. Well, so one of the questions about sort of computational language is, we're building this language to represent the things that humans want to talk about. And by the way, the thing I should explain is one of the big points of Wolfram language is to have a language that we humans can think in terms of, as well as a language that computers can implement. And it's sort of very important to me, at least, that this is a language where you can expect to read and think in terms of the language. If I were to say, I don't know, say, line plot, string length of, what are we going to do here? Let's say table, string length, Roman numeral, and let's see here, I don't know, n goes up to 200 or something, is now showing us. So let's see, what is this? This is the length of the strings that correspond to Roman numerals, a table of those for numbers from up to 200, and this is making a list line plot of that. And kind of part of the point here is that we humans can read this, and it's something where we can sort of think in terms of these kinds of constructs. And for me, I guess I've been using Wolfram language long enough that for me it is completely routine that I can start to type the language before I could ever explain to a person what it is that I'm trying to do. I mean, it's similar to fluent speaking of human natural languages, that the things that you just get to the point that you can think in the language. And one of the things then, a big responsibility of a language designer, in the way that people think about things, and ends up being determined by the structures that exist in the language. So, for example, I don't know, an operation like fold list. So, what is fold list? Let's take a range 10, and let's just evaluate that in place just so you see what it is. Okay, so fold list is this construct. So, once I introduced fold list, I don't know, 34 years ago or something now, one starts thinking in terms of fold list. And there are lots of kinds of things where I just kind of know that that's a thing that you do with fold list, so to speak. And it becomes kind of a primitive for thinking about things. And that's kind of one of the both objectives and an interesting outcomes of computational language, is this fact that you put these concepts into the language and they then become the anchors, that the sort of primitives with which you think about things. People often discuss that question for human languages, the kind of Sapir-Whorf hypothesis thing of do the structures of languages to determine how people think about things into those languages. That's been somewhat controversial for human languages. For computational language, I think there's absolutely no question at the answer to this issue. The way, and I can see this, look, people write Wolfram language code, and the way that think about things is determined by the structure of language. And it's something people have not yet realized. In a few decades, people will realize that language design is a critical determining factor in sort of how people think about things, but that hasn't really been realized yet. Perhaps the better, because otherwise people would put even more emphasis on just exactly how is this design working. I mean, as a language designer, one of the things that is interesting is when you assuming you get things right, there are very few people who comment on the design of the language. It's only if you ever get anything wrong that people say, oh, there's this very awkward thing, and don't like it, and so on. So okay, so let's talk a little bit about sort of the broader concept of computation. This idea of the operation of things according to computational rules. One of the things that has been, if you look at sort of the history of science, and you go back to sort of earliest days of science and antiquity, people usually the objective of science was to say what are things made of, to take the world and made of atoms, is made of vortices, made of whatever. It was sort of a very, very structural description of the world. The big thing happened in the 1600s was this idea that you can kind of wheel in mathematics as a way to describe the natural world. That's the state of calculus and then the mathematical sciences and so on. And the thing that was sort of a big question was was sort of the structural description of the world and the mathematical description of the world, was that the way that one should best describe how things work in the world? And back in the early 1980s, well, I had been doing, Rohan mentioned, I had been doing physics from when I was a kid, so to speak. And I got interested in sort of a bunch of foundational questions about the natural world, particularly about sort of how complex phenomena occur in nature, how things manage to make complexity and so on. And the discovered that sort of the things that I knew from mathematical physics and so on didn't really have anything to say about those questions. So I got interested in sort of is there a more general way to kind of think about formal models of the world? And that led me to realize that computation and computer programs are sort of a general way to think about sort of models of the world, and to think you can think of what happens in the world as something where you're doing an operation that's like a computational operation, what determine the successive states of the world. So the question was, if the world was sort of operating according to programs, what kind of programs might it be using? And so that got me interested in the question of, well, okay, what do simple programs typically do? You know, we're looking at programs when we write them in programming languages or whatever. We're writing fairly elaborate programs that are set up to do something that we specifically have imagined doing. But what if you just take sort of programs picked at random? What do typical programs do? And so that got me into looking at these things called cellular automata. And so this is a typical rule for a cellular pattern. It just, you have a line of black and white cells, and each step you determine the new color of a cell based on the colors of that cell and its two neighbors on the step before. And so, for example, here we might say, let's start off with a single white black cell. Let's run the thing for a few steps, and let's make a picture here. And so this now a picture shows the result applying that computational rule a bunch of times. We start off with one black cell, we just follow this rule over and again. This is what we get. So now you ask the question, okay, let's sort of think of the whole sort of computational universe, possible programs like this. So of these particular programs, there are just 256 of them, and we could, for example, just go right ahead and say, let's just try and make a table of all of those different programs and what they do. So just make this thing, we've got say make a table 0 to 255, and now we're going to make this the table of results, all these programs and what they do. So each one of these, we're just starting off with one black cell. Sometimes these ones stripes are the ones where they say that 0, 0, 0 turns into 1, 1, so they alternate success steps. But what we see is, okay, that there are some nested patterns that are showing up here for some of these rules. And then my all-time favorite science discovery is this thing here, 30. So let's take a look what this one does. So let's look at rule 30 here. There's rule, and let's just run it a little bit. That's what it does. And the very bizarre thing here is that even though this is a very simple rule, very simple to state, the behavior that you get once that behavior has been generated is something that looks quite complicated. So you can go on and let's run it for, let's say, 400 steps or something, and this is what we get. This to me was at the time a very sort of intuition-breaking discovery, because I had thought that when you have a sufficiently simple program, sufficiently simple rule, you'd always get very simple behavior, but it's just not true. In the computational universe of possible programs, it's absolute routine that very simple programs could have very complicated behavior. And so, for example, if we look at the center column of cells here, for all practical purposes, so far anybody can tell this time, that sequence is completely random, even though it was generated by the very simple underlying rule. Now, in essence, you can say, have you seen phenomena like that before? Something like digits of pi are like that. There's the rule for generating them, fairly easy to state. Once generated, digits seem for all practical purposes random. This is an example of the same kind of thing, that we're seeing it in this program sort of plucked from the computational universe. Just program number 30 of all abilities in the computational universe were already this kind of behavior. So there's much significance to this. I mean, in terms of nat science, the big significance is this seems to be kind of a secret that nature uses to make the complicated stuff it makes. That in the computational universe, it is very common to have simple programs that whose behavior is not simple. But there's a different kind of piece to this. There's a very general principle I call the principle of computational equivalence. That's sort of a way of characterizing what's going on in a system like this. And we can kind of ask the question, when we see a process going on, some kind of rule that's being applied, we ask the question, what sophistication of computation does that process applying the rule correspond? Is it something we could just say, oh, that's a simple mathematical operation, we know exactly what it is? Or is this sort of, what kind of computation operation is it? And the sort of big principle that I kind of developed in the early, I guess, late 1980s, is this kind of idea, above some very low threshold, all of these systems are equivalent in the sophistication of the computation that they do. So that means that, for example, this Rule 30 system is doing computations that are just as sophisticated as anything in the end, anything in the universe, or in particular anything that's now mathematics or our brains or anything like that. So, what consequences does that have? Well, one of the things you might think on the basis of kind of traditional science and the way people talk about science is about making predictions about things. And so you might say, well, we have rules, so we're in good shape in terms of making predictions scientifically about what will happen with the system. And this is in fact, the principle of computational equivalence, that's not how things are going to work. Because if we were going to make a prediction about what this system does, in a sense, we have to kind of jump ahead of it. We have to be able to do more sophisticated computing that it itself can. But the principle of computational equivalence says that we do that. And so that leads to a phenomenal computational irreducibility. The phenomenon that in order to know what's going to happen in a system like this, you effectively can't do that except by following the same kind of computation, the same computation, the process that the system itself follows. It's sort of an irreducible computation to find out what the system will do. So this is sort of a fundamental feature, I think, of many systems in the computational universe, that they exhibit computational irreducibility. Something in a sense that we already have a notion that there's a thing like that. For example, the presence of bugs and in programs is a common example of where it's hard to foresee, given the program you use from, it's hard to foresee what it will do. There's also kind of a more general version of things like Gödel's theorem and undiscernibility. So, for example, if I were to take an example of asking a question like, what will this system ultimately do? Here's a particular rule. This one happens to go on the left. You can say, hey, look at the system. It started off a single black cell. Now it's just doing all these. It's got all these structures reducing. What would actually happen in the system? Well, if it wasn't for computational irreducibility, we could expect to jump ahead and say, we're much smarter than this. We can figure out what to do. It's going to halt in the end or not. But because of computational irreducibility, we're basically stuck following every individual step in the system to find out what it'll do. And in fact, in this particular case, after about 4,000 steps, it becomes fairly clear what the system is going to do. This particular system is an example of one where we know for sure that this system is capable of doing computations that are as sophisticated as anything. We know we can make a universal computer out of this kind of system. It becomes a bit more obvious if I just show kind of a random initial condition here. Let's show it for 1,000 across. Okay, there we go. So here we're seeing we're seeing these structures that are kind of interacting, and we can kind of imagine maybe we can implement logic operation, something like that, with these structures, and indeed one can. These kinds of things, a bit like particle physics, with all kinds of collisions and collision rules and so on. And indeed, that's also a good analogy to going on here. But in any case, so this kind of realization that there's this computational universe out there of possible programs, and even simple ones can do very sophisticated things, was sort of a big discovery of mine in the 1980s, and it sort of led to things. It's led to using programs as kind of raw material to make models of things in the world. That's a useful thing. But it's also led to the realization that, for example, there are programs that you can mine for the purpose of doing useful computation. You can discover, for example, Rule 30 is a very good random number generator. It's something which was in fact just mined out of the computational universe. So one of the things to realize is that within the computational universe, there's sort of amazing capability of different kinds of things that can be done, different kinds of programs that can be created, and so on. And when we think about computational language and its role, one of the ways to think about that is that's kind of a bridge between what is computation possible out in the computational universe, what we humans can think about and care to think of, so to speak. Computational language is this kind of thin of possible computational ideas that are the ones humans at the current state of technology actually care about. What's interesting to me in the development of Wolfram language over the year is that really certain kinds of constructs become a bit more familiar to people in general, and they become things that you can reference in creating a computational language, and can actually as a useful concept in the language. See, one of the things that is sort of critical in the creation of Wolfram language as a computational language is, if it wasn't for natural language, we would not have been able to create computational language. Because if we'd been if every one of the concepts that we dealt with was just, it's function number 317, nobody would have a hope. No, none of us humans would have a hope of understanding kind of what was going on in a computational language program. But we're leveraging the fact that we have kind of a collective societal knowledge of what words in natural languages mean, in the case of Wolfram English, and we're leveraging that sort of collective knowledge to be able to build something that is an understandable computational language. One of the questions that arise thinking about sort of representing the world in computational terms is okay, well, what is the world ultimately made of? And this is something that long interested in, but to my surprise, there was sort of this huge progress made 3 years ago now in understanding kind of what fundamental physics is made of, and I think we need a really very good understanding of sort of the framework of how our universe is built. And I think we can say with considerable certainty now that the universe really is computational kind of all the way down. And so let me talk a little bit about kind of what we now understand. And this is an sort of emerging, developing area. And Rohan mentioned multi-computation, which I know he's been working on, and maybe I'll talk a little bit about that. It's kind of the sort of leading edge of what we're thinking about here. But let's talk a little bit about what the universe is made of. So last couple of thousand years, there's been kind of this idea that ultimately what's in the universe, space. And what is space? Well, space really isn't anything, just something that puts stuff into. You say in a Euclid type fashion, there are positions you can put things in space. Space itself isn't a thing. I've just been studying as it happens. There's the things about thermodynamics happens. I've been interested in for like 50 years now. But finally managed to bring together some things that I thought when I was like 12 years old. So I'm excited about that. That's my excitement of these last few weeks. It's funny because in the mid to late 1800s, people were talking about, when you have a material substance like water or something, what's it made of? And everybody said, well, a lot of people said, well, it's just continuous stuff and it's not made of anything. With this kind of group of people said, no, actually made of atoms and molecules and so on. And it's kind of funny to see that some of the earlier arguments for why space is not made of anything are the exact arguments people making in the 1800s for why things like water are not made of anything. But I think what has been clear is that space, like water, is made of stuff. And space is made of what we can think as atoms of space. What are atoms of space? They are purely elements who only characteristic is that have an identity, that every atom of space is different from every other atom of space. I have one more feature, which there are relations between atoms of space. So these atoms of space in our universe are 10 to the 400 maybe atoms right now. I don't know exactly. We don't know. No, we need to know one parameter from experiment to know the answer to that question. We don't know that yet. But these atoms of space are related to each other. So you have this giant graph, actually better represented in terms of a graph, that represents the relations between atoms of space. And so our whole universe is just this giant hypergraph. There's relations between atoms of space. And so everything that is us, the electrons, photons, and quarks, and so on, that we're made of, all of those things just have to be features of the structure of this hypergraph. So it's a little bit like if you say something like water, you've got a bunch of molecules bouncing around, but within the water you can have things like vortices, eddies, and so on, and then those have some kind of vector, some kind of structure that sort of rides on top of the underlying thing of all these molecules bouncing around. And so it is with the physical universe and particles and so on. We don't yet know details of how electrons are made from these graphs. We have some ideas about, but we do not know the detail of that yet. Sort of the big achievement is even to understand how the structure of space is structured. And just like these molecules bouncing around fluid on a large scale, the fluid satisfies the equations of mechanics. What we discovered actually in the 90s is that these kinds of networks, the large scale behavior of one of these networks follow the equations not of fluid mechanics, but Einstein's equations for space-time. So, for example, phenomena like gravity arise because of the structure of this hypergraph and features of this hypergraph. And we know nothing about this hypergraph at the beginning. We don't even, there's nothing that says it's embedded in three-dimensional space or anything like that. All we know is there are these elements and these atom space and these elements are related in certain ways, and we can then start to, every other feature of the world is emergent from that structure. So one of the things that's important here is how does this network, what happens to this network? Well, what happens is that it follows rule, and those rules basically are just like the transformation rules that we provide more from language. From language, we're taking tree-structured symbolic expression, we're applying transformation rules to them. What makes the language. So in our universe, what makes the universe is that we're taking the hypergraphs and we're applying transformation rules, which are essentially rules for hypergraphs. We're applying that over again, and the thing that we make is a big hypergraph that corresponds to the structure of physical space, the structure of the universe. In a sense, of these models, there's nothing in the universe except space, and everything we know about is a feature of space, of the structure of space. But so it's sort of interesting that this kind of computational idea of transformation rules for symbolic expressions, these particular symbolic expressions seem to be the ones that represent the actual physical universe, and the transformations of those symbolic expressions represent, what do they represent? They represent the progress of time. And so in this system, in our world, what's happening is time is a progressive computational process. The passage of time is the doing of irreducible computation. So computational irreducibility is the thing that causes time to have kind of a hard, meaningful structure, so to speak. It's the thing that is the sort of progression that happening that we experience as time. Okay, so one of the things about these transformations is that there's a particular transformation rule being applied. One of the things that can happen is there are many different places where that rule can be applied to this hypergraph. And so how do we deal with it? In Wolfram Language, one of the kind of unspoken facts, not unspoken, but one of the things that kind of was a thing I decided in the early design of the language is that basically when it's making transformations for symbolic expressions, and at any given moment, there might be multiple transformations that could be made for the rules one has for a given symbolic expression. The decision of the language was just make the first one can, and just keep doing that until one reaches a fixed point. That's the option of Wolfram Language. you type an input, it has certain rules that can be applied. You have the first one that applies, you keep that until you reach a fixed point. The fixed point is the answer. That's we return to the user as the output. Okay, so that's kind of the thing to do. What happens in physics is a little different, that there are many rules that can be applied, and we can imagine applying any one of those rules in order. So what we are getting, this whole multi-way graph, we call it, that represents the possible history of the universe responding to different possible rule applications that can be made. And so that multi-way graph, these are some representations of multi-way graphs, these represent different paths of history for the universe. And so at any given moment, there could be a particular state of the universe where there are multiple future states, multiple next states corresponding to different rule applications. And some of those next states could merge, and there could be states of the universe that were distinct, but then there's a merged version that arises later. Okay, so what? Well, so what that's what gives quantum mechanics. Quantum mechanics is kind of the big difference between classical mechanics and quantum mechanics. And quantum mechanics, sort of definite thing happen in the world. In quantum mechanics, there's this whole collection of possible paths. You get to say what the probability of certain things having happened on different paths are. What happens in models of physics is this multi-way graph is the thing that gives quantum mechanics. And so what's happening is a little bit brain twisting to understand, but basically what's happening, there's this multi-way graph and it's forming, and at any given time we can take slice across this multi-way graph. At any given time there are many possible states of the universe. There's kind of a map of the entanglement states of the universe, the relations between the states of the universe, that is a map that is laid out in what we call branchial space, the space of quantum branches. And this is a kind of space, it's not like physical space, it's a different kind of space, but it's a space which has certain properties in common with physical space. And one of the things that happens in branchial space is that we have a certain extent in branchial space. Just like in physical space, we don't get to sample individual atoms of space. We're pretty big compared to the atoms of space. And so we are sampling kind of aggregated features of the atoms of space. And that's we conclude that the universe behaves the way it does is because we're looking at sort of aggregates of what's going on. And by the way, the sort of the key phenomenon underneath, there's all this computational irreducibility going on. Sort of the key fact is that to computationally bounded observer like us, who isn't able to see all that detailed computational irreducibility, is only able to get a computationally bounded view of what's on. To an observer who has that feature and has one feature, which is that observer who believes that they're present in time. So we are made of these atoms of space, just like everything else in the universe. And as time progresses, we're made new atoms of space. So it's a non-trivial fact that we believe that we are persistent in time. We believe there's the same us that exists at subsequent moments in time, even though we're made from different atoms of space. So with those two things, computational boundedness, belief in persistence in time, looking at this computational irreducible substructure leads necessarily to some laws of physics that correspond to the ones that we observe in space-time and so on. Well, a corresponding result over here in branch space basically involves we are kind of entities which are sort of branching, merging brains. And the question is does a branching, merging brain perceive branching, merging universe? And sort of somewhat the same reason, computational boundedness, belief in persistence time, we can conclude things about the structure of what we have in this multi-way graph, and the things we can conclude respond to the core of quantum mechanics as it turns out. But in any case, so though this kind of idea of branch space, there's this kind of notion of us as observers embedded in branchial, so on. Now, if we really want to go to the absolute depths of the rabbit hole, so to speak, is the following thing. So one of the things that had long confused me was let's say we make models like this, and eventually we say we found the rule for the universe. And we can write it down at some little thing that says you transform a hypergraph like this and so on. Say that's the rule for the universe. Then the next question will be, why did we get this rule and not another one? And so I found that very confusing a long time until I realized that in fact the way to think about this is that just as a particular rule is being applied in all possible ways, so we can think of all possible rules as being applied in all possible ways. So instead of getting a multi-way graph that's representing the possible applications of a particular rule, we have a real multi-way graph, the ultimate multi-way graph that represents the application of all possible rules, possible ways. And so that object thing we call the ruliad, and the ruliad is kind of the sort of the biggest computational thing you can make. It is the entailed limit of all computational rules applied to all possible computational initial conditions. So, for example, we could do. Let's say we do that for Turing machines. Let's pull up a picture of that. We could. Let's see here. Let us say we're looking at some. Let's give an example here. Well, that's kind of an ordinary Turing machine, just running a particular Turing machine rule. That's a multi-way Turing machine. There are multiple possible rules that can be applied at every step, and we get kind of branching Turing machine. But we keep going, and we can say let's run all possible Turing machine rules, and then we'll get this of the ruliad represented in terms of Turing machines, and so these are some samples of that. And we can go and look at well the structure of this thing that is sort of entangled limit running all possible machines from all possible conditions for a time. To say, well, how can there be anything interesting in such a big object? But the critical fact is that we as observers of the ruliad are also embedded within the ruliad. So our experience of the world is based on kind of sampling a piece of the ruliad from within the ruliad. And so one of the big questions, and this, I told you, this is pretty deep in the rabbit hole. One of the big questions is what kind of experience does a different kind of observer have in this ruliad? And what we realize that there's sort of a physical observer who had the experience of the ruliad is physics. That same thing that is the ruliad is also the foundation of mathematics. And the different kind of observer, a mathematical observer, where the experience of the same, the ruliad, now gives you the structure of mathematics. So, for example, if I were to look, let's say I have an example. Let's look here. This is big thing I wrote recently about the physicalization of mathematics. The same kind of structure, the same multi-way graph is what you get if you take sort of expressions and you're applying axioms to those expressions to transform them into other expressions. And for example, we might have a proof that this is equal to this, which would then correspond to a path in this multi-way graph that goes from one particular expression to another expression. And we can keep going, and we could look at all sorts of different kinds of things here. We can really ask about mathematics in general, sort of what is the layout of mathematics in meta-mathematical space. When we look at every node is a theorem of mathematics, and how is theorem of mathematics connected. And so we start looking, these are theorems of logic. We start looking at kind of the connections between theorems of logic, the Euclid's stuff. Someplace here I have some pictures of those are kind of breakdowns of operations like plus in terms of lower level computational constructs. But we can have someplace here, I think I have a picture. Yeah, these are pictures of meta-mathematical space showing the positions of certain famous to humans theorems in meta-mathematical space. But the key point here is that the ruliad is the underlying thing that underlies all of the mathematics, just as it underlies everything we have in physics. And as we are sort of our experience doing mathematics is a particular kind of observer of the ruliad. Our experience doing the physical world is another kind of observer of the ruliad. Okay, so let me try and bring all of this a little bit together, because one of the things I've been working on a lot recently. How do we take this idea of multi-computations? And so this idea that there isn't one thread of computational experience, many threads of experience. How do we take that and think about that in practical terms in computational language? So one of the features of multi-computation is there isn't just a single thread of this is the computation that happened, this is the answer you get out. Instead, it is necessary to have an observer in order to conclude anything about what's going on. By the way, a lot of styles of programming, like something like logic programming, is you're following all these different possible paths, and you're asking, does one of those paths end up in a particular property? Or, for example, for theorem proof, it's about there are many possible ways you can apply the axioms. Is there a path that will get to the particular theorem? Or probabilistic programming, there are many different possible things that can happen. What is the kind of mirror of different things that occur? That's kind of a density and branch kind of question. But so one of the things that I've been currently interested in is sort of taking the idea of multi-computation and making it humanizable, so to speak, finding the analog of constructs like fold lists and so on that represent multi-computational kinds of ideas, and see how that works. And it's sort of an interesting thing, because in Wolfram Language, as I mentioned, the basic workflow is input, compute, output, always following kind of one particular transformation rule. So in multi-computation, we wanted to follow all possible transformation rules. We want to kind of understand what kind of construct you get out. To give you an example, I wonder if I have an example here, of just sort of a frontier of this kind of thing. Even the question, let's see whether we have this. I'm not sure we have this yet. Let me see. We do not yet have this. I'm going to show you a little of what the innards of a computation look, and the way to present kind of progress of computation by a kind of computational graph, and sort of the correspondence between that computational graph. There's sort of single-way version of that computational graph, the kind of thing we have today, and a multi-way version of that computational graph, and trying to understand kind of how one thinks about things in that sort of multi-computational way. By the way, this whole multi-computation question is sort of the core issue of distributed computing, where if you have multiple operations that can happen sort of at the same time, simultaneously, it's the sort of question of how you think about that. When do you have kind of race conditions where it matters that this particular operation had happened in front of that one, and so on. And it turns out that it seems that there's a close correspondence between kinds of things that one thinks about physics and reference frames and things like that, and the kinds of things one has to think about in distributed computing when one thinks about programming in a distributed way. So there's so kind of a frontier for me is thinking about well, when you have multiple possible computational direction for a computation, which ones do you follow? Does the computational front look like? How does one characterize sort of the way people probably know depth first search, breadth first search, and so on, as ways to scan and graph or a tree? What is the general way of representing sort of how one makes progress in a computation? Now, it turns out that question has been seen before. It's been seen in general relativity, because that question of what that front looks like is precisely the question of metrics and the labeling of space-time in general relativity. And it's a complicated issue, but it's a place where there's sort of this analogy, physicalization one can do. And there are things one knows about event horizons, holes, things like that in the general relativity case that one can import into this kind of computational case. Well, anyway, that was a very kind of rough and rambling iteration of a bunch of different computational ideas that you guys will find interesting. It's always a little bit challenging, because I'm here. I'm a bit transmitting into the blind here because I don't know what you guys exactly are interested in. Now I'm about to find out that you already knew all of this stuff. And please, if you have questions or comments, I'd be happy to try and address them. Looks like there's one hand up from Christopher there. Christopher.
Yeah, I have a question about dimensionality, because I mean, suppose you're to say that the universe is modeled by this graph, which is one of the hypergraphs in the ruliad, and then space is coming from the connectivity of the graph. It seems likely to me that if the connections are being made according to those rules, you'd expect it to have fractal dimension. Like, I mean, if you were to do like a breadth first search starting from one node, and you were to ask how many nodes do I reach as a function of the distance I search, why would you expect that to be an integer power? Because in our universe on a macro scale, we always seem to see exactly 3 dimensions.
Do we now? That's a question. That's actually one of the interesting possible things that will be an experimental indication of our models. We're pretty sure in our models that the universe starts infinite dimensional and gradually kind of cooled down to be roughly 3-dimensional. If you ask the question, kind of what do you actually get? Let's take a look here. Let's see. Let's look at what you actually get. So, for example, here are some rules that are running that have particular structures. You're absolutely right in your sort of way of thinking about how to compute dimension, and think about it in terms of sort of a geodesic ball. You start at a particular point in hypergraph, and you graph distance r away, and you ask how many nodes you reach, and you fit that progression to r to the d. Say d is the effective dimension of the system, and in many cases the effective dimension. I don't know. Let's try this one. It's just running this. It'll run fairly quickly. I think this particular one is 2.6 dimensional end. But let's look at different things. So, for example, here's one. Let's try this one here. This one, another that's just a hypergraph transformation rule. That particular one produces this graph structure, which you might reasonably recognize as being kind of like a 2-dimensional structure. So you get all sorts of different kinds of structures. Sometimes they will be fractional dimensional. Sometimes they'll be infinite dimensional. Sometimes the dimension not converge, and sometimes they will be approximately integer dimensional. The question of whether, and this is for example where it's integer dimensional, but it's space. You can you get all kinds of different structures that are asked. So the question of whether you why you get integer dimensional is a very interesting question. We do not know the answer yet, and the extent to which our particular this relationship between us observers of the universe and the universe that we are observing. And it may very well be some characteristic us as observers of the universe necessarily implies an integer dimensional space as the one that we perceive the universe to be constructed in terms of. Because we don't need to. The fact that we believe in 3-dimensional space is kind of a feature of the way that we sense the universe. We wouldn't necessarily have to believe in 3-dimensional space. If we were, for example, if we, I don't know, if we experienced the universe only, we didn't have eyes and we experienced the universe only in a different way, we might be able to parse the universe in terms of computational process, which didn't really refer to dimensions. The fact that 3 dimensions is important to us may be something that's quite dependent on the particular sensory apparatus that we have, things like this. But we don't know why. We do not know why the universe is to a good approximation dimensional. It is an interesting question whether the universe is exactly 3-dimensional. I guess that it's not, and that there are fluctuations, and probably in the universe, as I mentioned, it probably was infinite dimensional. It is very likely that dimension fluctuations survived up until 100,000 years after the beginning of the universe, which is when microwave background sort of separated off. And so it's pretty it is quite likely, if we only knew what dimension fluctuations would look like astrophysically, there is a good chance that we can go and try and detect them. But this is one of the sort of physics challenges in our physics project, is figuring out like how do photons propagate through fractional dimensional space. yes, it's a, I mean, to know to get a characterization of sort of, even at the level of hypergraph writing, what the effective dimension of what comes out is non-trivial. By the way, I'd say that when you have a system like this is locally like a Euclidean space, it's fairly to think about doing calculus on the basis of this. It's fairly easy to think about what is the manifold structure that you get from the system. The thing that remains a big challenge is when the result is a fractional space, what's the analog of calculus in fractional dimensional space? You know, when you study calculus, you might study univariate calculus, multivariate calculus, but you never study fractional variable calculus, and nobody knows what that's like. And so one of our big projects actually in the next 6 months or a year is to create kind of a generalization of calculus that can apply to these fractional dimensional spaces, and that even usually in manifold, the ultimate model at the sort of lowest level is Euclidean space. We don't have that here, and so we need to construct something that can work. And my expectation is there will be some properties. You already know this. There are some properties pretty generic to different hypergraphs, and there are others that depend on the limiting structure of hypergraphs. But it's a one has to generalize things like I don't know things about how curvature generalizes to fractional dimensional space. We need sort of finer details of differential geometry in dimensional space. And I think there's going to be some super interesting mathematics that comes out of that, as well as being important for physics. And one of the features of that is things about whether the presence of topological obstructions like particles, how that depends on the effective dimension of space, et cetera, et cetera, et cetera. Lots of interesting questions. Study them. You should study them. It's a one of the things that happens in science is that there are occasionally there are these sort of methodological advances that occur, and then there's about a 5 or 10 year period when there's a large amount of low-hanging fruit to be picked, of all kinds of obvious questions to be asked. And I think we just hit very fortuitously kind of hit this very sort of vein of mineable science. And so we're sort of in the middle of that period when there are a lot of interesting things to study. Another question here, Rafiq.
Hello, Professor Wolfram. Thank you so much for your presentation. You probably don't remember, but I also asked you a question during the World Science Scholars event with you. And
okay.
So my understanding from your presentation today with regards to the hypergraphs was that we can apply certain rules to symbolic representations of the universe and then extrapolate that in terms of how the code plays out to determine different trajectories of the universe. And my question is, how do you initially decide upon those rules to apply? And how does that look like in terms of the actual code in actuality?
Well, this is one of the points that very confusing thing is like, what would be the rule that is the rule for the universe? And what you realize is all rules are rules for the universe, and is us as observers of the universe who are sampling a particular slice of that of ruliad contains the consequences of possible rules. And so that's it's some sense we are making, in some sense we're making our own version of reality. I think a way to that, it's a bit abstract, is in this rulial space. There in the ruliad there are this sort of these pods that correspond to sort of slicing the ruliad with this according to the operation of many different possible kinds of rules. And in a sense, every one of those slices, every one of those positions in the ruliad corresponds to a different point of view about how the universe works. And different observers would have different points of view about how the universe works, even though all those points of view are embedded with Ruliad. And there, I mean, this is a deep rabbit hole, but a deep rabbit hole still not fully ended by any means. But one of the features of Ruliad is that there are a phenomenon called causal invariance, which means that even though you may have two quite different descriptions, there is a sense in which certain conclusions that you make will always be the same, even those those descriptions are different. So I think you're asking, how do you pick a particular rule? And the answer is you don't. All possible rules are part of the ruliad, but what is happening is that a particular observer is, by the virtue of, in a sense, their position in rulial space, is effectively picking a particular rule by which to describe the universe. And so I suppose one way to think about this is, if you think about kind of different minds considering the universe, you can think of those different minds as being in different places in rulial space. So just as, different, one could be, different critter, alien intelligences or whatever, be placed at different places in physical space. So too, they can be placed different places in rulial space. And so I can, every different mind exists at a different place in rulial space. So in a sense, we'll have our internal representations of the universe that correspond to our particular way of parsing the universe based on our position in real space. And so there are a lot of very wild things that you realize, like for example, you have two minds that are at different places in real space. You think of that like in a slightly more practical way as, two neural nets that have different internal representations of the world. And the question then is how do those two neural nets communicate? If they can't do sort of a brain-to-brain transfer because they've got all these different, a billion different weights for the neural net and so on, what is the way that you communicate between those two different sort of mind-like entities? And what you realize is that concepts, the robust idea of concept, is the thing that is kind of the analog of particle in rulial space. So a particle electron is a thing where space, there is this thing that is persistent, that sort of exists as an electron through time and space. And so similarly in this rulial space, the thing that I think exists sort of independently through time and space is some kind of notion of a robust concept. That's incredibly abstract. Sorry, that this is not I think yeah, I'm not, I suspect it will be the case that we've managed to find, we managed to home in on classes of rules that, with respect to our current way of describing the universe, are a good way of modeling the universe as we currently describe the universe. Now that I say that in a rather tricky way, because as our technology increases, as our kind of Siri domain increases, there will be features of the universe that we start to think about and notice that we never noticed before. And as that happens, the things that we want in order to describe the universe as the universe is, will that change. But I think that will be undoubtedly the case that there'll be a model in this framework that we've made. There will be better and worse models that describe the features of the universe. Say, oh yeah, we can identify there's an electron here. There's certain features of three-dimensional space and so on that can be identified here. There will be models that are good fits for the ways that we choose to describe the universe, and hopefully over the next few years we'll home in more and more on what details of those models actually are. So a few thoughts there. Sorry, this is a deeply abstract subject.
No, thank you so much. I appreciate it.
Let's see, another hand up here from Bernat.
Yes, even though I'm really interested in the translation between natural and computational language, my question is about hypergraphs. And I read about hypergraphs around the same time I read a story by Jorge Luis Borges, which is the Library of Babel. Are you familiar with this?
Which story? I've certainly
the library,
heard of it before.
the Library of Babel.
Oh yeah, yes. People mention this story to me, and I have to always remember how the story works. But remind me.
In the most simple term, it's imagine a library that contains all the books with all the possible strings.
Yeah,
okay?
yeah, right.
So when I thought about the ruliad, it seemed to me that observing the ruliad would be like finding a book that contains a specific string in the library.
Right. There's a big difference between the ruliad and this library. Okay, the big difference is the ruliad is a dynamic thing that has in this library. is if you're enumerating all possible strings and you're asking, here's a particular string. In ruliad, okay, let's see how to say this well. The point about the ruliad is it is a computational process. It is not the ruliad representation of infinite computational process. The library is a sick representation of this thing where there are a bunch of strings in it. The ruliad is something where, as you kind of explore the ruliad, there is your kind of the ruliad is being unfurled, sort of infinite computational process, and it is how to say this. I mean, I think that the big difference is that it is one thing to say, I will enumerate this collection of strings. It's another to say, I will have this collection of computational processes. And the collection of computational processes is, which you might say, well, it's all possible computational processes. They're not independent. Why are they not independent? The reason they're not independent is because observers of those computational processes equivalents different that happen. Example, let's say hypergraphs arrive, and those two hypergraphs are isomorphic in the sense that you just relabel the nodes hypergraph and that same hypergraph, just like what was that for graphs. To an observer of the hypergraph, to the system itself, you might say those are different hypergraphs. They have different presentations, but to an observer, those two hypergraphs are necessarily the same. They are isomorphic, and so the fact that there will ultimately be an observer of the ruliad makes it be the case that it isn't. It has this entangled structure that is very different from the kind of just the straight. We will enumerate all of these different possibilities. There's probably better ways to say this.
The problem I find with this is that in mathematics you have, for instance, a vector space and a dual space of linear transformations over that vector space, and they're deeply connected. And you're telling me that there is not the same connection. There's not the same dual connection between possible strings that, if you interpret it in some way, would explain computations and these computations. There's not an isomorphism.
Yeah, the difference between the program and the running of the program. That's the main lesson of functional irreducibility. There's a difference between a program and what you get by running the program. It's not obvious that will be the case. It could be the case that as soon as you have the program, your work is done. You just say, here's the program, now we're done. But computational irreducibility means there's something irreducibly different between the pure underlying seed, the program, and the unrolling of what that program does. And I think
that continuity is it's like a transformation. You could transform that. I wouldn't say continuity because it's discrete. You could say that a book contains all the steps of transformation applied to a simple graph, and progressively contains all this information.
Right. The point is that what you're doing is you're crushing infinite to zero, basically, and that's that when you crush computational irreducibility to nothing, there is nothing left, and our experience of the world is experience of the process of computational irreducibility. So you can say, well, that's not very interesting. I just want to crush out computational irreducibility and reduce it to nothing, but then you just reduced out our whole experience of the world. And that's probably, insofar as we're interested in describing the world, we probably care about having a representation of our experiences of the world. Now, I mean, to go even more down the rabbit hole, beyond the ruliad, there are hyperruliads. So the ruliad is this construct that is a construct of computation. You could also have, hypercomputations where basically whatever it takes in an infinite for a standard Turing machine, we just say we just get something which says the answer in one step, and that's a hypercomputation. And we can have hyperruliads that are be a ruliad. Why we don't care a hyperruliad is because there is never communication between the ruliad and the hyperruliad.
It's a paradox. To observe this hyperruliad, it's a paradox, you could say.
Well,
Like,
I
it's
don't, I'm
interesting
not
to-
sure that, I think the point is that there's an event horizon between the ruliad and the hyperruliad. Just as an event horizon within the ruliad, there are black holes which have event horizons. And so an event horizon means there is no causal connection between what happens outside of that event horizon black hole. So the hyperruliad, the ruliad appears like a black hole. And to the ruliad, there is no way to, with the ruliad, there's no way for us to detect the effects of the hyperruliad. Now, why am I bringing this up? I'm saying that to the hyperruliad, everything about our distance is real. So let me say it a different way. So in a black hole, in a kind of black hole, in our models, time simply stops. So, for example, time is progressive application of these rotational rules. In the case of our black hole, non-rotating hole with space regularity, what happens in the system is the rules no longer apply. So what does it mean that the rules no longer apply? It means time has stopped. There is no more computation going on. So to us, looking at those poor critters that are stuck in the black hole, time stopped, it looks like, it's very boring, nothing is happening there. Now, similarly to the hyperruliad, so the critters in the hyperruliad, what's happening in the ruliad looks solely boring. Would be the case that what to us is our whole experience, that's our whole computationally irreducible experience of all of time will be crushed to nothing. And so you can say, well, I want to enter mathematics, or I'm going to crush all of time, nothing. But then you've kind of removed all of our experience. That probably isn't what you do when you're thinking about science for humans. I think that's going on here, is that you can say, and by the way, to make it more technical that might be of interest, something I've really recently in category theory, which you may or may not know about, but category theory is kind of a kind of a high level representation of mathematical processes where you think about objects and morphisms and so on. Category theory has this idea of transformation from one thing to another. There's this morphism and another morphism and so on. One of the key axiom of category theory is the idea of compositionality. The idea that if you have a morphism from F to G to H, that there's also a morphism directly from F to H. That idea is a mistake, in my view, because what has happened is that category theory is basically denying computational reducibility. It's if there is a way to get F to G, G to H, there is also an equally easy way to get from H. And that sense denies computational reducibility. That's why category theory can make conclusions. That's why there's decidability in category theory, and you can actually make mathematical deductions in it. It is also why it can't be a representation of the richness of the world as the world is, because it essentially has crushed out computational reducibility. So I think, I'm now making a slightly more succinct answer to your interesting question about the library of Bab or whatever. I think this is the difference between the computational process and the mere data contained within that process is computational reducibility, and that's the nature of our experience. And you can choose to not be interested in our experience, and you can invent mathematics which crushes our experience to nothing. But that's probably not science, so to speak.
Yeah, what you said about computational reducibility, it's actually one of the things I was thinking on the last part of the presentation. So it ties up very well with the reasoning I had. But I'm deeply terrified by all these concepts. Like, I must admit that this is deeply terrifying for me, but still it's interesting.
Well, I think why do you find terrifying?
I find it terrifying because there's an obfuscation every time you go up or down in a level of reasoning or analyzing a system. Like, if you analyze humans as a system, you go to a higher order, you can find simpler relations or that arise from very complex beings that we are. And the same happens with with particles, you can go up and down levels, and there's obfuscation. And this is going a lot of levels deep. And
Yes.
the thing is, isn't it possible that it obfuscates a possible reality? Because it's trying to explain with simple rules complex behaviors, and these simple rules may also be explained by complex behaviors that are in turn simple rules.
Well, I mean, I think the things about the ruliad is it looks like it really reaches the end. It you know, in terms of our existence, the only, you know, this is basically saying everything is computational. It's not hypercomputational. We exist in the ruliad, not in the hyper-ruliad, and this is the sort of everything is describable computationally. It's computational all the way down. Now, the thing that is a little bit disquieting for science is you might have thought, based on kind of the you know, 17th century science or something, you might have thought that science would just give us answers to things. Science would let us kind of always be able to jump ahead and say, this is how the system will behave. This is where the planet will be a million years from now, or whatever else. What is said, as soon as you have complex irreducibility, that idea disappears. You cannot do that anymore. It is no longer the case that you can always look at what happens in the world and say, I know what's going to happen in the future. Now, at some level, that's disquieting, that's disappointing, because it means there's a limitation, there's a fundamental limitation to science. On the other hand, from another point of view, it's rather satisfying, because if that wasn't the case, then, you know, we lead our lives, we go through all this time that we experience and so on. If it wasn't the case that that was computationally irreducible, we'd be able to say, forget leading one's life, forget the passage of time that we experience. The answer is 42, just go off and be happy, so to speak, right? And in other words, there would be nothing would be achieved by the passage of time by our experience. So the very fact that there is computational irreducibility it gives a meaning to the passage of time, which would exist otherwise. Passage of time would be meaningless. If it's possible to always jump ahead and say, and the answer is such and such, there wouldn't be this kind of hard nature to the passage of time. So I that as being a rather that's an interesting feature of the universe. Now, I have to say that things like the concept that in the end it'll just ruliad and it's all necessary. So in other words, we might have thought that it would be exciting to find out something special about the universe. We drill down and we figure out we got universe number 1316, and we feel very excited a bit about the fact that we are in this very special universe. The story of the ruliad is that will never happen. In other words, the thing that makes our universe is utterly generic. It is a necessary. The universe, one of the things that's conclude this thinking about the ruliad is this question of why the universe exists. And this is a philosophically complicated question. Why is there something than nothing? Why is anything actualized? What the idea of the ruliad implies is that the universe necessarily exists. That is, that because the ruliad necessarily exists. The ruliad is not something where you could say it might be that way or it might not. It's just like 1 + 1 = 2. Once you've defined the concept of 1, you define the concept of plus, inevitably 1 + 1 = 2. And so similarly, inevitably, the ruliad is what the ruliad is. And so then the only question is, in that setup, the ruliad necessarily exists. The issue then is, are there observers in the ruliad that are sort of horizing it and having an experience of it? And that's the sort of contingent fact of the world is that we are then observers of the ruliad, and it's how to say this well. But this real-time philosophy is not easy. The thing that the point here is that there is no longer to explain in why the universe is actualized. That's the main conclusion of this thing, that the ruliad is a necessary object of which we are sampling pieces. There are many sort of philosophical implications to this, but I think this point about the fact that the universe is, in a sense, what we make of it. So let me give you a few other little sort of philosophical tidbits here. So one question is, we exist at particular places in the ruliad. We are sampling the ruliad according to a certain set of assumptions about how the world, about how we sample what exists in the world. As our technology improves, and as our ideas, as our paradigm span, so to speak, so we get to sample larger and larger regions of the ruliad. That is, we can have a better view of what happens in the universe as our sensory and knowledge capability expand. You might say, well, that's really good, and time there will be sort of our civilization will gradually understand more and more broadly the nature of the ruliad. One of the things that I realized recently is, in the end, you have to be careful what you wish for, because in the end, if you were to expand your domain of experience, sort of be the whole ruliad, you would no longer exist, because in a sense, the nature of our existence is as a feature, sort of the coherence of sampling just a particular aspect of the ruliad. I mean that's the
paradox of observability, in a sense. You can't observe the whole system from inside the system. In the sense that the role, if the system rules your observance, you would need more rules to observe the whole system.
I mean, a lot of what comes out in our physics project and in our mathematics project is a consequence of trying to think through what it means to be an observer who exists within the ruliad, made of the stuff that is the ruliad. So the simplest version of that is the derivation of special relativity in our physics project. Comes about because, okay, so to sketch that one, the main issue is, let's see. The main point is that all you can ever sense about what happens in the universe is the causal graph of what events influence what other events. So you might say, they looked at outside the universe. You could say, this is what is happening in the universe. This update had happened, this update happened, that update happened. From outside the universe. So in extreme case, the universe might be a Turing machine, where one update is happening at any given time anywhere in the universe. The whole operation of the universe is just this Turing machine head running around updating parts of the universe. So you might say that's a crazy model of the universe. That can't possibly be right, because after all, I'm talking to you. You seem to be being updated. You and I seem to be experiencing time together. But the point is that you couldn't know that, because you don't know whether I've been updated until you've been updated. So all that ultimately matters, you've got this Turing machine head, it's running around. From outside the universe, it looks like the universe is doing kind of a depth traversal of things or something. It's just exploring one thing at a particular moment in time. But you are an entity embedded within the universe, then your experience is different, and your experience is based on the causal graph of what event influenced what other event. And that's kind of the beginning of this kind of notion of an observer of the universe experiencing the universe. And I have to say that these different kinds of observers in physics are very time-based observers who have this experience time where we have, we remember the past. We believe we are present in time. That's important physical observer. I think the mathematical observer in mathematical space is much more spatially oriented. Mathematical observer basically trying to accumulate, here are theorems I believe are true. And they're trying to sort of shove in a bunch of theorems they believe are true. And that's a somewhat different way of experiencing what is ultimately the same underlying reality of the ruliad. So, I mean, look, there's much to figure out here. But this is you can. I mean, I think there's a. It's been sort of interesting in the last I don't know months actually. Then seems to have been a rapid increase in the number of philosophers who've gotten interested in the ruliad and its implications. And unfortunately, things that happens when you invent stuff is that pretty soon people write about the things you've invented, but you're not able to understand yourself, and that's rapid happening here. But
I must say that philosophers will be really interested in looking at the ruliad as God, because the argument you said about the ruliad as a concept exists, then it must exist, because
yes.
we can think, we can come up with a concept. Is the same argument that throughout history people has given for the existence of God, because we can think that the concept of perfect exists, and then perfect must exist, and then God must exist.
Yes, all right. Yes, indeed. People have been. A bunch of people have been looking at this, and I think the thing that is a little bit strange from the necessary existence of the ruliad, like has been argued in theology, the necessary existence of God. What becomes contingent is our existence. What becomes obvious is our existence, which is kind of a side of kind of the sort of the reach version of theological arguments. This is is the does God exist argument flip sound to well, that's surprising. What's surprising is that we exist. And yes, there's a I mean, what is interesting from a sort of meta intellectual point of view is that a lot of these questions about sort of ruliad-like questions are questions that were asked by theologians 1,000, 2,000 years ago, 1,500 years ago, and so on. And those questions got completely submerged in modern science, and they haven't been asked for a long time. And so this is sort of what the thing that we're now doing. We've sort of drilled below the layer of sort of mathematical science, and we're back to the same questions that were asked 300 years ago or something, that are, in a sense, closer logical concept questions. They are questions that they don't look like the kinds of questions that are like mathematical science. But yes, it sounds like I'm excited to find them that there are an number of people who seem to be interested in these ideas. It's a very
I read about this after my physics Olympiad, and I found it really interesting because it connected some of the things I liked most. I found most interesting, be it physics, mathematics, and philosophy. So it was a match. But yeah, thank you.
I think that the thing that is right now an example of a challenge. I mean, I think you guys are the theming of this event, I think, is around programming languages and so on. And I think one of the things that is the challenge right now is to take, this increasing understanding we have of sort of how the world is together, and apply that, and so that we can bring that into something that is of sort of human technological sequence, so to speak. And sort of, we can turn that into a way of thinking about things that we can use technically as a sort of an computational language. That's what a way many aspects of what we're talking about that are beyond current human sort of paradigmatic thinking. The question is, the goal of language in general has been to take ideas and somehow concretify them to the point that people can think in terms of them. And so the challenge we have now, can we do that for multi-computation, for these things about the ruliad and so on? Can we invent kind of a way of thinking about these things that becomes routine for us humans? And that's the current challenge. Well, okay. See, so we should probably wrap up here, but I'm
Yeah.
You guys are all just black stairs. You could say hello, perhaps, and as a moment of where are you all from? Distributed all over the world. Are you all in
I think, yeah, distributed all over the world. There's a number of people from India and the US, as well as Spain and Europe. There are a few people from South America too. So some people have a very late or very early, unfortunately, right now.
Fair enough. Well, good stuff.
Yeah,
All
thank
right.
you so
Well,
much.
you can, I encourage, by the way, for people who are, I have to give, Rohan already gave a little bit of a pitch for this, but we have our high school summer camp for people who are still in the school age range. And we also have our school for sort of grown-ups and we also have a winter school, actually. We've been doing about the physics project and also now about our mathematics project that I guess will be coming up in a few months. So by all means, check out those things. You guys have had some questions that you should learn more about this. Good stuff. Okay. Well,
Yeah, thank you, Stephen, so much for taking the time to talk to everyone. It's a very engaging talk. I always love your talks because they're always interactive. And I think it's just so fun to see you type away in the Wolfram language and watch what comes out. So I really enjoyed it, and I think everyone else did too. So just wanted to thank you for taking the time to share that with us.
thanks. Okay. Bye-bye.
Thank you so much.
Bye.